today we are going to see the design of tubular connections. I think so far you might have understood little bit clarity on tubular member behavior. I think we have spent about 3-4 sessions. The circular shape helps in transmitting several loads in a better way compared to other shapes. Does not have torsional buckling, which is one of the greatest advantage, and the shape gives you a advantage of uniform sectional property in any bending direction. So quite a few which I think we stacked up in the starting of tubular members. Same thing also have a similar advantage on the connection itself. If you remember, or if you have seen connections elsewhere, for example, if you have a concrete beam to beam connection, beam to column connection, like if you see here in any buildings, we do not have a special design as such. You actually cast it monolithic, simply have a mold, the column is coming and the beam is coming, and you have a concrete poured in a monolithic casting method. Whereas in steel structures, it is not going to be exactly that. If it is a I beam to I beam connection, you may have several ideas how you want to actually transmit the loads. We have to decide. Now if you look back, we have a plate, and if you want to connect another plate, you can do a penetration weld, basically weld from both sides or weld from single side depending on the design. And you also can do a bolted connection by simply having a cleats bolt onto the receiving member, bolt onto the connecting member. So similar ideas, once you do that, then you need to make sure that the connected parts transmit the load successfully. For example, if it is a welded connection, the weld should have sufficient strength to transmit the loads from the receiving member, the vice versa. Basically similar idea when you talk about a pipe to pipe connection. How do we achieve that? That is what we are going to discuss. This is going to be little crucial. In a sense, most of them are empirical, very similar to structural member tubular design what we did. Every one of them is empirical. If you start from axial allowable stress, bending stress, buckling, hoop buckling, axial buckling, every one of them is derived from experiments, because the analytical method of response characterization is not feasible because of quite complex, number one. Number two, we are using elastoplastic characteristics. So mostly we will actually find out the ultimate strength by means of experimental studies, and then from there we derive the allowable strength by dividing by factor safety. So here in tubular design, it is a similar principle. Every one of them is going to be highly empirical, means we rely on what was done in the past by experiments and take that results, extrapolate the results to our situation, and that is where we need to be a little bit careful, because they may not have done testing to your scenario what you were doing just now. Previously nobody would have expected that you will do this. So basically limited amount of experiments were available. From there researchers have developed some useful method of design. That means you should design within the perimeters of restrictions given by them. You cannot simply come up with a design which is falling outside the parameters that they have defined. So that is where you have to apply your ideas to play within the range that the design is permitted. Of course, if you go outside, then you may end up on a case by case basis, do your own studies, means you can do an experiment, you can do a finite element analysis, or otherwise like what we are doing in our laboratory wave flume. If you have gone to our wave basin, whenever a situation is complex and unable to describe by the theoretical methods of responses, we always conduct laboratory wave flume test, just to make sure that our assumptions are valid, the responses are in line with what we have assumed, so that you feel comfortable. And if there is a difference, then you correct your theory. The experiments are not conducted to correct the experiments. You understand the idea, no? The experiments in any wave flume or in structural mechanics lab is to verify that your proposed theory is reasonable to predict the response. That is the idea behind doing experiments. Otherwise, some people may be thinking, we keep on doing experiments for what purpose? So basically in here there are two things we need to worry about. One is design against static loads, the other one is design against cyclic loads. So I have just listed down the things that we are going to look at. It is a very large subject, probably we will spend about 10 hours I think, because this is one of the most important subject in this whole subject. As I mentioned earlier on the day one, if the structural connections fail before the member fail, the whole structure collapses. You might have seen one of the picture, I think you may also see here. If you look at this particular connection here, what is shown here, oh, it is not coming, something like this. At that junction you can see nearly 9 members, if you count I think about 9 or 10 members are connected together. So, if the joint give away because of instability, because of local failure, you will see that all the 9 members will get disengaged and the structure will become unstable. So, you need to design the joint in such a way that it will never ever fail until all the members become plastic or near collapsing. You understand the idea. So, that means the factor of safety or the design constraints on the joint should be such that that should be the last one to fail. So, that is why we should give reasonable importance to the design criteria, understanding, and then application of parameters within the limits of what is being done in the past. Now, if you look at the whole thing, I have just given a list of things that we should know as similar to our design of members. We need to know what is the history of the joint prior to loading. So, that means you need to know how it was assembled, how it was welded, because they are going to affect little bit of influence on the strength, and how they may fail, failure modes. This is where is a more complexity is induced there, because the failure of a tubular connection is not that easy to predict. So, basically you will see several forms of failure, and it may happen or it may not happen depending on the parameters involved. So, we will just learn that and then try to do a simple classification pattern, what kind of shapes. I think once we go one by one you will know, and then we will look at the design methodology adopted by the current codes. You may see that they may be not logically correct, but we still use that method because that is the only possible way just now, because the alternative methods prove to be impossible at this stage, because this practical design becomes difficult. Then we will look at the empirical equations. Sometime I call it parametric or empirical, both are same. Parametric means the empirical equation in terms of a certain parameter of the system. So, for example, if you take a column, last time we were looking at allowable axial stress is highly dependent on one parameter, is KL by R ratio. So, that is one parameter. Now, if you look at any other parameter which is influencing, is the modulus of elasticity, which is governing the buckling, and the third one is the yield stress. So, 3 parameters are involved in that equation, isn't it? So, that is 3 parameter equation for allowable axial stress. So, this parametric equation is nothing but defining a particular response characteristic by means of one or more parameters. It can be linear, it can be non-linear, depending on what was the regression analysis you have done. So, basically parametric equation can be written for any type of behavior as long as you have sufficient information either by FE or by the experiments. Now, we are going to just quickly look at what API is asking us to do, because most of the design offshore structures either in India or elsewhere is adopting API universally, because it is well established for a long time. It is not that we are addicted to it, but there is no other choice, because we do not have a design code in house like you have design codes from Bureau of Indian Standards, several design codes for concrete structures, industrial steel structures or other mechanical components, whereas for offshore structures we do not have a code. So, we tend to use which was established earlier, so that we can use it, but in the recent times things are slightly changing. You can actually use ISO codes, which are international accepted codes, or you can use European codes or British codes. But historically I think for the last 30-40 years people have been using API for simple reason, that was the first one to establish, and they have actually done very good job. So, that is we continue to use it. And then we will also look at what particular material is susceptible to failure in the connections. If you go back to this picture, if you look at this, one important thing you will realize, each of the member is going to get loads from any direction. You just can't predict depending on the waves and the gravity loads. Some of them can be pulling away, some of them can be going towards the joint. Now, when you are pulling away, what happens? Imagine if you have a steel material, try to pull off. If the material is not 100% solid or without any pores or voids, what will happen? The material can come out. So, you need to have the material, selected material should have sufficient strength across the thickness. Normally, if you look at it, You know, if you look at a steel plate subjected to axial stress, it is going along the length of the plate, not across mostly. So that is one of the problem that we are going to face, that material selection in the joint is a special attention to be given. We will spend some time on that. And then we have few special areas of joints stiffened with rings, joints stiffened with grout, joints overlapped one on each, which you may find that funny, but then there are some situations where you will encounter that. So basically, this might take about 3-4 hours of lectures, and then we go to fatigue, which is maybe another 3-4 hours. We will go a little slow because very important area of subject. So as you can see here, I think most of you now familiar with the design of tubular members. Each one is carrying maybe axial, bending, shear, torsion and hydrostatic. So all these loads are resisted by members, and we have decided to check the member from one end to other at various close intervals, isn't it? Because the design process, what we discussed in the previous classes, is basically design means every section along the length must be safe enough to transmit the loads to this end and transmit the loads to the other end. Once the loads are transmitted to this place, for example, so what happens is the receiving member, so called the legs, you see here, this is very easy to understand where the loads are going. Ultimately the loads have to go where? It has to go to the foundation. It is not going to go to the sky, isn't it? So the loads are not going to go upwards. Every member receives the loads from gravity or from wind or from wave, and they have to transmit, and then they have to go downwards to the foundation. So that means if a brace member is like this, you can't expect the load to go upwards and then go to sky. It's not possible. So basically these loads are going to be going to the leg only, because the legs are predominantly larger in size. As you can see, more the stiffness, the attraction of loads will be more. You can imagine, you see this one member here, for example, there is a member here, that member is supported on one smaller member on left side and a big leg on the right side. So you can see the stiffness of the leg is more than the left side member. So by relative stiffness, you will see that most of the loads is trying to attract down to the leg, and that is where you will see that the design of joints here becomes. So the distribution of end moments or end loads will be going toward the supports. Basically stiffness, wherever the stiffness is more, the loads will get transmitted. In this particular structure, if you look at the whole thing, the whole structure, where is the stiffness? Stiffness is higher at the foundation only, because it is a very simple cantilever, isn't it? So basically that is why you can see here the more and more members, loads as you go down will be subjected to higher loads. So in this particular case, if you look at a particular connection, for example, I just taken one frame, one elevation from a 3-dimensional structure, I just have drawn one section in a simplified manner. So what is so called a joint or tubular connection means a receiving member is called a chord. This is just a technical name used by researchers and literature, and the member transferring load from elsewhere towards the joint is called a brace. So basically those members are all transmitting the loads to the joint, and the total assembly is called a tubular connection. Like if you look at a concrete structure, you have a column and a beam, also a junction, you know, basically a junction of beam and column is called a connection. Or if you look at an industrial structure, I-beam column or a channel or an angle bar also have a connection. So here we have got tube and another tube connecting, and basically that is called a tubular connection. And always remember, in offshore construction we do not permit bolted connections. We all cannot sustain because of the nature of environment we are in. If you have a bolted connection, if the bolt fails because of corrosion, because of movements, the structure will fail. So always we need to have 100% fusion welded, that means it is not even fillet weld, you need to have a penetration weld, which actually make the welded connection stronger than the parent plates. That is the idea behind. You have two plates, say 10 mm, 10 mm, the connection should fail only because of material, not because of the weld. So you go for a higher strength of the weld during the welding process. So basically fusion welding is only permitted in some cases, very minor cases, like secondary structures or above water top sides. You may permit other forms of welding, but not bolting. So this the terminology used in the design is basically cord and brace joined together in many of the forms which we will discuss later are called tubular connections. Now, you see here the difference between this picture and the picture that you are seeing just now is 3 dimensional. So, if you go into this junction here, you can see here if you take one plane, you got 1, 2, 3 members coming and joining, and if you take another plane perpendicular or on the other side, you will see another 3, and if you look at a horizontal plane, you may see another 1 member or 2 member or 3 member coming and connecting. Now, one by one you just slice off and see how the loads are transferred, but it is not that you can go and control the structure, you do not transmit the loads one together, you can't control. So, all the braces are going to deliver the forces simultaneously at any given instant of time, whereas the design process what we are going to plan is possibly designing a 3 dimensional joint is not feasible, because the design procedure developed today does not have provision to take into account all loads coming from all members in space. So, the design procedure adopted here in this last 20-30 years, we are going to design plane by plane, but then the interaction between plane 1, plane 2 and plane 3 you actually have a multiplication factors, the effect. For example, I have one brace in this plane, another brace in the perpendicular plane and another one in the diagonal plane. Basically 3 are going to deliver the forces simultaneously, but I do not have a design tool to do design by 3 together. So, what I am going to do is I will take the first plane, design it, design means find out the what is the thickness required, and go to the second plane and do the same thing, third plane I will do the same thing. So, 3 thicknesses I have, but none of them is correct answer, is not it, because I have taken only load from one direction and come up with a thickness of 10 mm, load from another direction come up with a thickness of say 12 mm, and the third one I might have say 15 mm, but each one is designed for only individual loads. What if I apply 3 together, what will be the thickness required? It will neither be any one of them nor you do not know the answer. So, what we need to do is we need to multiply some factors such that I will get a one thickness which will satisfy as if all the loads are supplied together. So, that is why the design procedure today what we have is treat individual planes and then automatically the design is satisfied if you follow the procedure given by the codes, because the codes have built in empirical factors which will take into account 3 dimensional effects. So, that is the design principle adopted. So, you must remember nobody could come up with a design equation for such a joint. In future somebody is going to design how many braces, nobody is able to come up. Of course, there are some recent research papers thinking about 3 dimensional joints, but then implementation by designers code still not yet done. So, basically as I mentioned earlier, assembly is simply cutting the pipe into the shape that is going to be received by the cord member. Imagine if I have one plate something like this, a flat plate, oh this is not a flat plate. If I have a flat plate, if I take one pipe and connect it, I will have a circular shape, simple circular shape cut. So, I can just weld it like this. So, if I draw it in the board, it will be very simple. If I have a flat plate something like this and a pipe so this is going to deliver the load here. Now, if I cut the cross section at this junction, so what will be the shape? Possibly something like this, basically you will see this. But if I make the pipe to be joined in an inclined manner, what will happen? What will be the shape of the plate, the shape of this section at the intersection? So, I will see a, what will happen? I will see a ellipse. All of you can understand, no? So, basically this is the inclined member received by a flat plate, a perpendicular member received by a flat plate. Now, imagine I do not have such a situation like nice plate like this. I have another member, this member is actually circular in shape. So, you can imagine the cut section at that interface is going to be a continuously changing profile. If you look at this yellow color shown there, is going to be a continuously changing all the time, because it's not a flat surface, it's a surface which is circular in shape, every time you will change. So, you have a very complex connection. That is why the design of tubular connections are quite interesting, because the behavior, if you see there, the stress variation is very large. So, if you could imagine this, I think then you can imagine right now how the connection is done. Remember, we are not going to remove the material here, this material will be there. Do not think that the intersection at this point, purposely I have made a dotted line here, because that material is not removed, something people might think, oh, it is like making a pipe flow, you actually remove that. Normally if you want to make a drainage pipe, so you remove that, it is not like this, that plate is not removed. So basically that is why you can see that dotted line is there, means the material is available there to transmit the loads. So basically that particular shape makes us more complex, because evaluation of stresses at this point, for example, if I just draw one plan view of, if I just have one view from this direction, I will just superimpose something like this. The plate may be fixed here, does not matter, something like this. If I look at the periphery of this point, 4 points or 6 points, if I apply a load of P, the stresses all around will be same or different? It will be equal, every point will get exactly same stress, but what stress we do not know. If you cut a cross section here, the stress in this point will be, isn't it, P by A, simple axial stress calculation. But when you come to the intersection nearby, there is a 90-degree change in the geometry of load transfer. You may see that this may be slightly higher than P by A, local notch effect, geometric effect, because it is trying to transfer the load by changing load direction. So the understanding here, the load is same, area is cross section is same, only thing is because of a 90-degree transfer I have a same stress. When I come here, what will happen? Will I have the same? I will apply P here. If I do a perpendicular cross section, I will see that P by A, little bit away, but when I come to the junction, I will not see that stresses are equal. I will see some higher stresses here, lower stresses here, different stress here, different stress here, because I have an inclination, and pattern will be symmetric. If I look at this is a center line, if I see the pattern here and pattern here, it will be similar, but what I will not have it is not going to be any more uniform stress. Now if you understand this, if you go back to that picture, it is a continuously changing surface, and you will see that the stresses are not going to be same, even though the load is only one load, you will find that, and that is basically the complexity introduced by the continuously changing profile of the surface of the pipe, wherein the tube is coming connected. So basic idea is assembly and welding is part of the fabrication. Basically what we do not want to adapt or avoid is the gap is to be kept smaller, we will see later, but not too large. According to the standard practice, we give a gap of 50 mm just for welding access, otherwise you will have weld on the second weld. Then the brace angle should not be smaller than 30 degrees, because you can imagine here, if I go here, if I make this angle 10 degrees, what will happen? I will not be able to access for welding in this place. So that is why minimum angle is 30 degrees. If it is less than 30 degree, it is not going to help transmitting the forces. And then the weld is always done from outside. Do not expect somebody to jump inside the pipe and weld, isn't it? He will be creating his own burial ground, because he cannot come out, isn't it? So, always welding is done from outside. Some cases if you have a large diameter pipe, but not for the braces, but for the main pipes, you may actually see people go inside and weld, but not for the braces. So, basically mostly we have a single V butt weld, that means only weld from outside.